So how do we make electricity anyway? We've talked a little bit about batteries and what batteries do. And if you took AP Chem, you've got a really deep understanding of what batteries do. That's one kind. That's where you take chemical potential and you turn it into electrical potential energy. But there's other ways of doing it. And the most common way in our society is actually to use magnetism. So we start out with a uniform magnetic field, just like this. All right, now I have to kind of hold this thing so it's not going to be the greatest. Okay, and then we have a loop of wire. Weird thing, we're going to talk about this, and we talk about this probably more in class, is if you change the magnetic field going through the loop, you can create a current. So we call that flux. So if you look, just imagine you're looking straight down in here. See there's that little ring there? Okay, now first of all, I should say I didn't draw this uniform field particularly well. It's clearly not uniform. The X's should be really evenly spaced, but whatever. So if I hold it in here, you can see the flux kind of stays the same, right? Just about the same number of X's in there. If I'm pulling the loop out, I'm having a decrease in the flux. In other words, the magnetic field going through the center. So nature does not like that decrease in the magnetic flux. So, and we'll talk about this when we get a little bit more into Lenz's law, we're going to get a current going around this loop. Similarly, if I take the loop and I start to rotate it, boop, like this, you can see looking down on it, here there's a lot of flux, and only focus on the X's that are in the circle. Less in the circle, less in the circle, less in the circle, less in the circle, less in the circle. None. Boop, increasing. And then, oh, decreasing again. Sorry, I'm trying to spin this and hold this at the same time. So when you change the flux, you can induce a current in the loop. The equation for flux is the magnetic field times the area times the cosine of theta. As you can see, each of these is actually pretty complicated. Flux is measured in Webers. That's something important to pay attention to. Magnetic field, of course, is measured in Teslas. Area is meters squared, but I do want to point this out. You want to only focus on the area of the magnetic field that is flowing through the loop. Okay, so if you start to pull the loop out, it's not like, even though the area of the loop itself didn't change, the area that actually has magnetic field flowing through it will change. So for example here, I have my loop here. Okay, the area of the loop isn't changing, but as I'm pulling it out, the area that is in the magnetic field is decreasing. So you just focus on that area, okay, not the whole thing. So what about that cosine of theta? What does that actually represent? That really has to do with, let's see, okay, like if we had a loop of wire, we think of it as lining up so that there's flux through that wire, or not lining up so there's not flux through that wire. So how do we kind of measure that angle? Okay, well, first of all, let's talk about a magnetic field. So let's say we have a magnetic field here, and this one is pointing up out of the page. Got an eyelash on there. Okay, so it's pointing up out of the page. And let's say that we took our loop, and I'm going to show you kind of a way to think about this. So our loop was like this, okay, and you lined up now so you can see flux through it. Doesn't have flux, flux, no flux, flux, no flux, do, 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 do. Okay, so to help you visualize that, I want you to imagine a wheel, a tiny wheel, right? And you see how the wheel has an axle here? we're going to call that the area vector. It's going to show us when it's lined up so that there's flux and when there's not. Okay, now this is a wheel. You can't see it through it. I just found it in this desk. If the area vector of the loop, which is perpendicular to the actual loop itself, see it's 90 degrees from the actual loop itself, is pointing in the same direction as the magnetic field, that is a cosine of 0. And the cosine of 0 is 1. If the loop starts to rotate, that angle changes. And we're measuring the angle from the direction of the magnetic field and the direction of the area vector. So now they're lined up, less lined up, less lined up, less lined up, less lined up, all the way until we get to 90 degrees. And you see when it's 90 degrees, cosine of 90 is 0. So we would say there's no flux. The equation for flux itself is actually completely useless in this class by itself. What we really care about is how it's changing. So if we want to measure the EMF coming out of a particular loop, we would say, okay, we're curious about the change in flux over time. And if we had multiple loops, for example, if you had a loop and a loop and a loop and a loop, we'd put a little n in the front to discuss, okay, how many loops are there. So that's what that n stands for. You could have the strongest possible flux in the world. You have tons of magnetic field going through a loop. But if that magnetic loop if that magnetic flux doesn't change, nothing will happen. You will not get a current in that loop. And just to review, because some of you guys were asking this question, remember EMF, the term appeared first in circuits. And that was kind of, at the time, I introduced as like a fancy way of saying voltage. But it was a reference specifically to this. This is electromotive force. And it's kind of, you know, the potential that's driving the current around the circuit. For all, you know, intents and purposes, you can use this just like you normally would with Ohm's law. V equals IR. You can kind of use it interchangeably. Okay, let's try this problem. It is similar to a homework question. A loop with a radius of 2 centimeters and 30 turns is positioned perpendicular to the uniform magnetic field. Over the course of 0.2 seconds, it is rotated 90 degrees. The coil has a resistance of 0.5 ohms. What is the current? All right, so we know, first of all, that the equation for the EMF is going to be change in flux over time. Well, they gave us the time, so we're going to have to figure out that change in flux. The equation for flux, if you recall, is BA cosine of theta. Let's focus on what's changing here. The magnetic field is not changing. The area is not changing. It's the angle we need to focus on. Luckily, they're kind of telling us two key positions. So originally, this was a coil in a magnetic field. It's positioned perpendicularly. So I'm going to just throw it in a magnetic field like this. So the coil itself is perpendicular to the magnetic field. This is really key. You might feel at this moment like, okay, well, if I were to imagine my area vector actually is perpendicular to the coil itself. So I think I showed you that with the wheel, so we could kind of imagine it's sort of pointing out of the page like this. That's what the angle is measured on. Right now, the area vector and the magnetic field are parallel to each other. So the angle here is actually 0. Cosine of 0 is 1. So we could sort of say this. All right. We have time. We're going to say, all right, B isn't changing, A isn't changing. What is changing is this cosine of the angle. So originally, it was 1. So we're going to say, okay, cosine of theta final minus cosine of theta initial. Okay, so VA, and we have cosine of theta. Fine, we haven't gotten there, but we do know that this was 1 over time. If we now rotate that loop 90 degrees, you can kind of picture its unit or its area vector is now going to be kind of pointing like this. Okay, if you think of it as a wheel. So here it was before, pointing straight at your face. Now we've rotated 90 degrees and it's going to point that way. Yeah, it also could have pointed to the right. I didn't specify. It actually doesn't matter in this problem. So now you can see that the area vector is perpendicular to the magnetic field. And that would make the angle between them 90 degrees. So the cosine of 90 is 0. So if we look at this, that means that 0 minus 1, this is negative 1, b a over t negative. That negative may freak you out right now, but I promise you when we get into the next section and we talk about Lenz's law, that negative is going to make a lot more sense. Let's just not focus on it for right now. So we have to go after the b and we have to go after the a. All right, so we got to go after the area. I'm running out of room here. Area is equal to pi r squared. Be careful because it's in centimeters. So area is equal to pi 0.02 squared. And math tells us that. So now we're going to plug that guy back into our area. They gave us the magnetic field in the problem. And we can just plug and check now. Okay, so we got 3 is our magnetic field strength. Our area is 0.00126. And the time was 0.2 seconds. And math gives us that. Boy, that is a pretty low voltage, but that's what happens when your teacher's tired and they just make up numbers. So now we're going to use that to find the current. So at this point we found basically what's the equivalent of the voltage, but we need the current. So we're going to use Ohm's law, and we're going to plug that in. So we've got 0.019 equals the current, and the resistance was 0.5. And math, that is a very tiny current. Definitely not enough to heat a Pop-Tart, so pretty much useless. But I hope you had fun doing it. I'm glad that you made it through this video. Here's a meme.